Okay, the recording. Let me click. Okay, the recording started. Okay. Then I'm just going to introduce you. Hi, good morning, everyone. Good evening, Prof. Chakhalian. My name is Wang Xiao. You can call me Renshou. This morning, we are very fortunate that we have Prof. Chakhalian to give us a presentation on quantum material. Prof. Chakhalian is a full professor in Rutgers University, USA. He got his PhD in University of British Columbia, Canada. He focused on quantum material, including correlated systems, and he's a well-known researcher. His expertise is demonstrated partially by his excellent research papers in, for example, Science, Nature Materials, Review of Modern Physics. Actually, Prof. Chakhalian was a visiting professor at NTU, I believe, in 2012 to 2013 during his sabbatical, I believe. I hope he enjoyed the climate here, which is a bit warm. And also before the talk, I discussed with Prof. Chakhalian. I told him that the audience would be roughly half expertise and half general audience. So that means he designed his presentation in a way that a lot of general concepts would be properly introduced. I think this is great because I believe for expertise, a new perspective would be introduced. And for the general audience, I believe you will enjoy this joyful experience. I think that's all I want to see without further ado. So let's welcome Prof. Chakhalian. Please start.
Okay. All right. Xiaowang, thank you very much for inviting me to give a talk. And it really brings good memories when I heard from you. And Christos Panagopoulos was my host, and it was fantastic experience. And we just exchanged recently emails yesterday. He couldn't be here, so. But yeah, no, I enjoyed not only the weather. I also thoroughly enjoyed just basically the whole physics department. To me, the building was spectacular. It's really spectacular. The way it's located, the labs and the students, their lifestyle, everything was really great. So hopefully this madness will be over soon and we'll start sort of visiting each other again. Well, anyways, let me get started, and I'll share my screen, and if hopefully everything will work as intended. Is it coming? Okay. So is everything good? Is it good? Okay. So the title of my talk is Novel Topological Phases in Synthetic Magnets. It sounds very scientific, but I'll try to make it as simple as I can, and I try to aim a sort of a level of physics today mixed with the scientific American. So if you have any questions, I was told that you can put them in the chat, or if you want to discuss some opportunities with what I'm going to show to you, please feel free to contact me by email. I put here as the website. This is the website which shows what we're working on now. But I'll briefly start with the good picture, because first of all, I would like to make an acknowledgement. This is not the work of one person. It never can be, because I'll show the immense complexity of what we do. Many people got involved. I absolutely astonished by their talent, their contribution to this project. And so today I'm going to be sort of like being a voice of this group of very talented collaborators. This is my group, which I try to sort of make a potpourri, sort of the combination of people who work in my group, and I'm very happy to have very talented people like Liang Wu. He's now back home, and Sharon Liu. He's also back to Beijing. Some people. Danny's just got the position in Netherlands. Olga is I believe that she's now in Princeton. So people moving, and I got two new talented students, one from Taiwan, it's Fangqi Wu, and Michael Torelli is a New Yorker. So that's sort of like, there are more people in the group now, so we move in and everything. So I'm the PI for Laboratory for Artificial Quantum Matter at Rutgers. I formed it in 2016. And I want to show you that the way it looks now. So we got 3 pulse laser depositions, sometimes they know as laser MBE, molecular beam epitaxy. This is the machines where you produce nanofilms. Basically, that's how you grow them. Then you have to characterize it. A lot of stainless steel here. We have X-ray photo emission built here. We built also very recently, put online the medium energy EELs. That's a new spectacular techniques to study excitations like plasmons, for example. But we've been adventurous during the COVID-19 pandemic. We decided that it's maybe the great time not to be, put all our effort down. Instead, why we wouldn't ramp them up? So we decided to spend immense amount of money. I was fortunate to get support from my university. So we built over $1.5 million new instruments, and I want to show it to you how it was designed. So this is, in my view, the only instrument available today which combines angular result photo emission. This is the sketch; it's not a real thing. So this is the AutoCAD drawing. This is the angular result photo emission to study quasi-particles in your quantum materials. But what makes it unique, we have angular resolved, absolutely high energy electron, inelastic electron diffractometer built into this whole thing. And it operates down to 6 Kelvin. It has all other nitty-gritty things. And of course, it's connected in situ with the growth. So not only you can study the quasi-particles like many groups can do, but we put online this angular resolved high energy inelastic electron scattering things to study all possible excitations. Now, so what can you study with this? By the way, that's how it looks like. So that's how we spent 2020 and 2021. So that's the new monstrous thing. By the way, to tell you how monstrous is that, it's 11 feet tall, the whole thing. So it really looks small on the picture, but it's gigantic. So that's people who do photo emission, they can recognize that's the ARPAS thingy, but it's just to show that it's really not as pretty as, like, look here, it's really complex instrument, and it's unique in the world at the moment. So what can you study with that? What makes it unique is just sort of like a little advertisement. What are we gonna get? You can study everything from the usual thing, some quasi-particles, the band structure, we call it a Schrödinger machine. It allows you to basically see the dispersion of electrons inside your quantum solids. But what makes it unique is this part, is the angular resolve, not only photo emission, but angular resolve inelastic electron scattering. And then you can study everything with a resolution better than 1 milli-electron volt. That's a sort of like a real extreme. It's getting very close to what optics people can do. We can study electronic state excitations. We can study many body excitations, including magnetic ones. We can study the charge transfer, excitations, Hubbard excitations. It's all sort of things. And of course, you can do diffraction. It's built in inside. That's a typical thing. And here's the example. Those are phonon modes in high temperature superconductor, as seen in this angular resolved inelastic scattering. So this is really very much comparable to what people would see in neutrons. So this is really wonderful. It's a tabletop, you would say, resonant electron, inelastic electron scattering, or inelastic neutron scattering. So kind of complementary. Okay, enough for the advertisement. So what I'm going to talk today is about the topology. I don't assume that you really know a lot, and I found that many people hear the words, but they rarely sort of have the opportunity to really understand what does it mean. So let me start with the slide, which I sort of would like to say, topology is not new in condensed matter physics. This is not just a pretty picture. This wonderful creature. The name of this creature is Bojum, or Bojum. It depends how you pronounce it. This is the early work from Lewis Carroll, The Quest of the Shark, Snark. This is the creature from this text, which has very strange mouths, which looks like a singularity. And as far as I understand, Marmin, the same Ashcroft Marmin, the second person in that thing. So Marmin proposed to use the topological states in the helium-3 based on this creature called Bojum, because that's how the topological lines, those are singularities in helium-3 look like. That's really like sketch, and I made them as like look like glasses for that thing. But the term Bojum is a real name of the topological singularity in the helium-3 liquids. So, but people studied that in the domains and the ferromagnetism. They look at the dislocations in the crystals. Those are all topological things. Liquid crystals is particularly a remarkable example of the topology. You can find that, but that's not what the topology I'm going to talk about. Now we're going to talk about something very different. And so the topology entered this solid state physics in 80s. And what happened there, they discovered a quantum Hall effect. When you take two-dimensional heterostructure made of semiconductors, you place in the high magnetic field, all of a sudden you see your resistivity or conductivity when you do specific kind of measurements being quantized. And it was very bizarre and so strange that people got awarded Nobel Prize. And then there was like another installment of that called the fractional quantum Hall effect, another Nobel Prize. And it's all been realized as the sort of reincarnation of topology. But then in 90s, there was another sort of installment of topological ideas. They came from understanding that a lot of things we thought being sort of classical or semi-classical or quasi-quantum, they could be really explained in terms of some strange things like Aronoff bomb effect kind of things called Bare Phase, and I'll talk about that. Later on, it just gave basically birth this ideas of curvature of momentum space, gave birth of many, many interesting ideas like spin Hall effect, anomalous Hall effect. Then cold atoms came online, being used as a kind of simulation engine for theorists. And then finally, we arrived into the graphene and topological insulators and some kind of spintronics where people utilize not traditional sort of spin, but some properties related to what's called the topological currents. And the future. So what's the future? The future is, of course, saying that we could use perhaps this fundamental research and move to the areas where we can do something really useful. For example, topological currents would be a wonderful thing because they're dissipationless. They could be wonderful for topological electronics. Of course, spintronics can be used now in the quantum computing as an engine. If we understand how to work with fractionalized particles, we can start thinking about room temperature superconductivity and the traditional understanding of strong correlations would give rise to what's called the motronics. But that's all sort of like, you know, anybody can guess what it is. Now, I want to focus today on this, basically topological states and what can we do with the topological currents. This is the picture perhaps everybody is familiar. I found it so been abused, but it's a wonderful picture, basically showing what topology is about. This is the one of the, by the way, reincarnation of topology. There are many, many different topologies. So the best way to look at the topology is to start with this kind of objects where you could basically calculate very, very simple thing. You take any figure like this, you triangulate it, and then you count the number of faces. the number of edges and the number of vertices. And you can make this number of faces minus number of edges plus the number of vertices. You would be totally shocked. It doesn't matter how many trianguli we'll put on the surface, it always will be the same number, absolutely the same number. And I'll tell you what this number is going to be. That number, it doesn't matter how many triangulars you break these things into, it will be always number 2. So that is the first example of Euler characteristic of the topological invariant. So you triangulate any figure, you calculate this, and this thing is independent of what's the triangulation, only depends on the intrinsic topology of this object. So in other words, if I do this triangulation on the torus or do triangulation on the sphere, my answer will be completely different, but it will be like a real integer number. And we like integers. Integer means it's protected. So it is real, something intrinsic. The most important thing to realize for you is there is a absolutely unbelievable theorem which says if you calculate if you triangulate any object like this into this and calculate faces, edges, and vertices, you can do it much better and much simpler by simply looking at this object and saying how many holes it has. This hole's known as genus, or I just call them a hole. So how many holes it has? This object torus has 1 hole, sphere has no holes, 0. So then you can calculate number 2 minus 2g, 2 minus 2 number of holes. And it will be exactly the same as calculating this Euler characteristic. But wait, there is even better thing. The Gauss-Bonnet Theorem is it's a marvel of differential geometry, which says if you take the local curvature of the space, so there you can write the formula in terms of x, y, and z, and calculate local curvature of your object. Then if you integrate over all surface like this and divide it by 2 pi, that will be exactly equals to the 2 minus 2g, the number of holes, and exactly equals to the same Euler characteristic if you just simply triangulate your object. Is that not really spectacular? So you calculate curvature, you just simply plug there a number of holes, here's the 2 holes, or you just triangulate the object, it will be all the same. So it is real topological index. Okay, that sounds good. But that's where you typically end your story. That's your topology. But this is not what we're interested in. We say, what's in it for me? How it enters the solid state physics. And here I'm giving you one example. So this is the space where typically solid state physicists think of. You go to the momentum space. We don't think of real space, we go to momentum space. And the crystal is made of periodic arrangement of atoms, right? So periodic arrangement of atoms, it means that they're a periodic boundary condition. So what are we going to do now? We take our lattice. There are no electrons. It's just a lattice. It's the space where the electrons will live in the future. But at the moment, it's just a lattice with the periodic arrangement of atoms. And because periodic boundary conditions, right, it's instead of doing the infinite thing, I just glued this to that, this side to that side. So you see, I made this kind of hollow cylinder by gluing this to that because of periodic boundary condition. It gives me a cylinder. And then I take these points on this side again, because this and this is periodic as well, right? And glue them together. And as a result of gluing, I got the torus. So because of periodic boundary conditions, this to that and that to that, I got the topology of the momentum space with the periodic lattice is really a torus. Okay, so, and we know that torus has this genus, a number of holes 1. Okay, that's already very interesting. Okay, so let's build on this. I'll take my object, which is a trivial band insulator. And for trivial band insulator, we have this electrons will occupy all the states here. This is the unoccupied states here. This is a conduction band, and they're separated by the gap. So in order for the electron, to get from occupied states to unoccupied, you have to jump across the gap. And whatever we do, this gap survives. Like let's presume. So what will happen if I place my insulator into the vacuum? Well, very simple. Vacuum is equivalent to the sphere. So their vacuum is nothing particular. It's a sphere, and it has the genus equals to 0. So no holes. But this structure, this topological insulator, also has nothing interesting in there, and we can show very simply that this any band insulator, in fact, is equivalent to a sphere as well. And so now we have inside, we have a sphere, topologically sphere, and in a vacuum is sphere. And if I have a surface here, I'm going from genus equals to 0 to genus equals to 0, nothing happens. So placing topological, non-topological insulator into the vacuum does nothing. You will still get the same thing. And that's what we've been doing for the last 70 years, studying all this kind of insulators. But now, let's say I have some strange insulator here, which has inside the band structure to be in, or the electrons move in kind of momentum space, which is equivalent to torus. But the vacuum is still sphere. And here's the interesting thing. You cannot go from torus to sphere without punching the hole in the vacuum. So punching the hole means that I need to move from genus equals 1 to genus equals 0. And somewhere here, so in other words, I have to punch somewhere a hole, and it happens, vacuum is this, the bulk is that. Then on the surface, I have to cross the genus equals to 1 to genus equals to 0. So somewhere on the surface, I have to change the topological properties, because going from inside of the crystal to the vacuum requires me to punch in the hole to change the genus. And that is topological reason why on the surface, I will get new states. So in other words, I have to cross the Fermi edge, I have to cross the gap, and on the surface, because I have to go from two different topological indices, I have to cross it by basically crossing the gap. And this is what's the reason we have surface states. So placing topological insulator, which is the insulator with non-trivial, non-spherical genus, non-spherical object inside, into the vacuum automatically guarantees there will be edge states. Okay, simple. That's what's called the bulk edge correspondence. So the Bare Curvature is another very important thing. So now we have our topological object, so something like this, some surface with a momentum space, and I want to move my electrons. So this is what I'm doing. I move my electron. This is the wave function for the electron. It moves here in the momentum space by some value delta k. And let me show it to you. So I move it by the value of delta k. So a little bit here. So this is my momentum. This is the state. And I move a little bit here. And so once you move by delta k, you can just basically write these things that it's just the expansion. It's the same value, plus it's a derivative, right, of this wave function multiplied by the delta k. That's trivial, right? But then if you say, how does is this wave vector overlaps with that? How much overlap you have? So you just take basically this combination, this u of k, you overlap with this value right here, and then just multiply from that side by the value of this state. You get 1 here plus this little term, and then you realize that's actually the Taylor expansion. That's the Taylor expansion. So you can write it as a Taylor expansion. So this now, so this state overlaps with that by basically changing the little phase. And this phase is just term. This thing is known as a Bare connection. In other words, Bare connection connects state with UK with the state which is shifted by delta k. But of course, you know from your electrodynamics, perhaps you remember if you have some object vector field which is A of k, you can always create the new object, which is omega of k, which is just it's a rather a curl of this field, and that's known as the Bare curvature. So in other words, it's the curvature of the momentum space here. So as a result, I want to remind you from electrodynamics or electrostatics, you remember, this is the vector field on the path. It's from the Stokes theorem, you know, that you can convert it through the flux through the surface delta S. And as a result, you will get, this is the magnetic field. This is bizarre. Moving in the curved surface in the momentum space is equivalent of creating momentum magnetic field. So this thing, which is nothing but the moving in the curved space here, is really equivalent of creating fictitious momentum field. It is fictitious. It is living in the momentum space. But that's what it is. I want now to tell you. So once you move your electron, this is the state of the electron in some curved space, in any configuration space, in any momentum, for us important momentum. It's basically, as a result, the electron will experience the intrinsic fictitious magnetic field, which is basically just the curvature of the momentum space. That's remarkable. And just to show to you how useful is that, we place our electrons here. See this, the little arrows here on torus, for example. And we remember that torus has one hole, so it's 2g minus 2. So I place one here, it gets me the value of 2. And then we would just, one gives me value minus 1. And what happens here on this torus, we got singularities. You see, that tells me this, the theorem tells me that the sum of the singularities on this figure is equals to Euler index. So in other words, if I look at the singularities of this field, for example, like this, you can see those are monopoles. Then it means the sum of this singularities, which I say, let's say the singularity is value plus 1, the singularity is minus 1, that should be equals to the Euler index. And I have a little cartoon to show it to you. So how can you make it? If you have a constant magnetic field, then you attach a loop to this constant magnetic field and run the current here that it's produce the magnetic field in the opposite direction. Then you will generate, basically you cancel out the field inside, but you generate some kind of pseudo singularities here, which will look like, if you look at the cross section, looks like this. And that is basically where you create this monopoles. So you can really just have this, but imagine that all happens in the momentum space. And finally, I want to show to you something really very, very important. So we agreed the curvature of the flux when the electron moves in some closed path in the momentum space. It generates curvature. It will be like a flux of the curvature, gauge flux on magnetic field due to the curvature of this space. But the Gauss theorem says if you have non-zero flux through the closed surface, there has to be a source or the sink charge, right? So it should be charge inside. And I showed the example, for example, imagine I have a magnetic monopole. I know it's fictitious, but imagine it's a magnetic monopole. By the way, if you don't recognize magnetic field for the monopole, it's because it's in the momentum space. That's how a basic magnetic field of the monopole looks in the momentum space. If I just plug it here and integrate it, because I have to integrate the total curvature, then we'll get this, what's the famous topological charge or topological index is known as a Chern number. So in other words, if I integrate the curvature, the Bare curvature in the momentum space, which is equivalent to the Gaussian curvature and equivalent to the Euler index, that's the Chern number. So physicists call it Chern number, mathematicians call it Euler index, nothing else. It's the same thing. So the integrated Bare curvature around the whole momentum space gives me the topological index known as Chern number. And so for this particular monopoles, those topological indices will be plus and minus 1, and that's how they look like for this kind of vector field. It looks like inside the crystal we'll have fictitious magnetic field, and they will have different chirality. So they will be like a north pole and a south pole if you wish to, or we can attach the chirality for this electrons and that electrons. Okay, so basically we're talking about the degeneracy where the bands will cross, and how you quantify the solid topology. So finally, I'll tell you the recipe. So you start with your crystal structure like this. It's for the films. This is for the crystals. Then you go to your favorite theorists. They ask to calculate band structure. They will give you the bands. They will identify, for example, this is the material which I'm about to talk about. They give you the Weyl points here. And then what you do, you calculate Bare curvature. So you calculate Bare curvature of these bands, okay? And then you will integrate this Bare curvature across the whole Brillouin zone, across the whole momentum space. You identify the singularities with the topological indices called the Chern numbers. Simple. Okay, so let me just tell you about, are they real? The Weyl fermion and real materials are predicted by theory is humongous. Look at this. The number of materials in the topological materials database is 24, almost 25,000. Among them, they claim that there are 10,000 topological semimetals. Is that true? Well, not quite. So there is a lot of critique how it's been done. You know, it's been sort of like simplified. In reality, there are very few, and I've shown this as of 2019. Among the magnetic topological Weyl fermion materials, we have like a handful, 3, 4, 5. With inversion symmetry-breaking non-magnetic ones, we have a little bit more. So the king of these materials is known as a material known as an pyrochlore with the strange metal called iridium. Iridium, by the way, is one of the most expensive and rarest among the metals in periodic table. The annual consumption, if I understand this, is less than 3 tons, a year. So it's quite limited in supply. So then the group of Sergei Savrasov around 2011 produced a theoretical paper saying we have a recipe how to create the most sort of prototypical Weyl fermion material. And if you take a specific crystal called pyrochlore and place the iridium inside, and then you will get something mysterious called the Weyl fermions. Because remember, the Weyl fermions are not known in the vacuum. It's a holy grail of particle physics. They still search for that, but we don't have it. But inside the solid state materials, we claim we do have it. So I'll skip the recipe the way they did it, like I'll skip this sort of thing, but I'll tell you a little bit about this material. This material is very unique. It basically has this formula. You take a lanthonide, which is any of those particular elements like praseodymium, neodymium, samarium, europium, gadolinium, terbium, etc. Then you add a little bit of iridium inside, and of course you mix with the oxygen to stabilize those positive ions. And what's inside the crystal structure is quite complex, but most important thing, the iridium atoms, ions will be sitting, making this kind of tetragonal sort of structure, which is connected like this. For those of you who understand a little bit of condensed matter physics, what makes this material super unique is the fact that the spin orbit interaction here is gigantic. In many, many materials, it's barely milli-electron volt. This is so unique, where the spin-orbit interaction is reaching the same value as the bandwidth and almost the same as magnetization. So it's a Hubert U. So this is the absolutely unique material. What makes it even more unique is the way how the magnetic spins, the magnetic moments are located in this crystal. They actually create what's all known all in, all out. On this tetrahedra, all spins look at the center of tetrahedra like this. On the next one, we'll be looking all out. That's why it's called all in, all out, or 4 in, 4 out. So all in, all out, all in, all out. So it's kind of like a pattern, if you wish to. Why is it so interesting? I just listed here tons of papers. There's a Nature, Sciences, and PRLs. They all theories, by the way, where they claim you just name your favorite topological phase and you will get it in this particular crystal. What's the problem? What makes this material so unique? I want to show it to you something, just you will appreciate it deeply. So let's just look at the this sort of cross-sectional cut here. If you cut the plane here, you will get a lattice, what's known as a Kagami Lotus. So if you wish, it's a David star, or it's a Kagami, Japanese weaving basket sort of pattern. So imagine your electrons are hopping here. In the pyrochlore, what makes it so unique, the phase of iridium atom here for the wave function, for the black and the yellow, the opposite. So it's a plus, minus, plus, minus, plus, minus. That's the phase of wave function. Now, if the electron wants to move outside of this hexagon on this triangular, the white triangular, it can hop from this with the phase plus, or from yellow, which is phase minus. But they perfectly, look at this. This is a perfect structure, right? They cancel out. And that's bizarre, because now your electron is confined into the hexagon. Okay, no magnetic field, nothing. It's just because of the interference cancellation, you got electron current moving like this inside the hexagon. And here, that's what happens. So it's broken into this pattern. I just want to just show it to you. Do you recognize this? This is exact analog of graphene, because this is exactly the same hexagon. This is how in graphene you move in the same pattern here. Okay. And what's interesting in the graphene, of course, you have to apply magnetic field to be confined into this particular pattern, and that will give you a quantum Hall effect at the end, right? But here you do nothing. And then you have to think about that. If the electron is localized like in a molecule, right, it would have no dispersion. And that's what makes it famous thing. It has strange features. It has a band with no dispersion. It means the electron stopped there. So in other words, it's infinitely heavy here because it's flat. Then you will have, because it's really like your graphene, you will have direct points in the band structure. Those are direct points. And you have some Van Hoff singularities, which is like on the top. But this is what really just makes its material so strange. It has flat bands. It has direct points at the same time. So it's a good opportunity to study this thing. And I want to show to you what makes a Weyl metal in this particular class of materials. What makes it so important? To make it so important, you have to prove a few things. First, you have to prove that this material is anti-ferromagnetic with this specific magnetic order. Next thing, you have to prove that this material has very large anomalous Hall effect, which is due to the Weyl magnetic knots. Those are monopoles. They produce intrinsic current, intrinsic magnetic field. It will have something strange called Fermi surface arcs, but I'll skip in a moment. And the most important thing, it will have very strange phenomena. It will have a Hall effect without Lorentz force. In other words, if your electric field and the magnetic field, they both in the same direction, you will have transverse current. Think about that. How's it possible? Your magnetic field and electric field, they aligned, and yet you got transverse current. And the only explanation to that, it has to be something really strange inside. So what's the challenge? ARPIS is not possible because so far people could make only 10 micron size single crystals, very, very small. Neutron scattering, impossible because iridium is a very high neutron absorber. And transport, oh, bummer. You thought you will have some exotic effects, but this structure is cubic. And every pair of Weyl knots in the cubic structure basically cancel out because plus minus in the cubic symmetry gives you nothing. Some of these things give you sum of Chern numbers or some of this topological charge has been zero. So due to the cubic symmetry, even transport cannot reveal much. People thought about that's hard, and they say, well, why you wouldn't apply uniaxial pressure? Just break this cubic symmetry. And then maybe, the special pair of Weyl knots will be, along this pressure direction will be revealed. People tried it, unfortunately, not very successful. Another strategy was proposed by a Japanese group. They say, why you bother with this pressure? Why you wouldn't grow thin film? Just grow the thin film along this direction. And the surface, there is a special direction, right? There's a surface. And so in this X and Y, it's the same, but the surface during the growth direction will break this symmetry for you. And so that was their proposal. And if you do that, you'll have, this is the direction where you grow your film. This is the momentum space, the Weyl knots. You will be a special pair of Weyl knots along this direction, which will not cancel out, and it'll give you a very large response in your transport, in some exotic photonic response, and things like that. But you need to grow thin films to break the symmetry of the crystal. And I'll be brief here, and I'll tell you this is the huge problem. I'm just showing you the number of reports where people attempted to grow these films. Let me show to you what's the real result and reality when they reported wonderful magazines. But if you're an expert, I'll just show you the show and tell. Whenever you see the spots like this, it's basically the cross section of your material, and you looking at the spots. That's whenever you see the spots like that, it means those are defects. Not perfect crystallinity, misalignment of planes, all sorts of problems. This is from the publications I showed before. Typically, people put those things into the supplementary. And you know why. But that's, we decided to take on that. It took us almost 4 years to try to solve it. And I'm happy to report today we did it. We solved this problem. So this, I put here the recipe, but that's for the people who wants to know, but this is the result. So this is the result. The films were routinely produced in our lab. As you can see, this problem here was solved. This is the substrate of your crystal. This is the film. It's perfect alignment. It's a 1-1-1 grown film. I'm showing how the interface looked like. Very, very beautiful. So I'm happy to say after 4-year effort, I think we're done. So we nailed this material. With this material, the next question is, okay, you have ultra thin film. Do you have this unique magnetic order? Because that's what makes this Weyl fermions inside. Once the magnetic order appears, the Weyl fermions appear. I'm just showing some really lots of papers been published about this. And then you ask, is there any paper published in the hundreds of papers, is there any evidence for magnetic order? And the shocking thing, nobody measured it. We don't understand why. Either people tried, they couldn't see it, but no one reported this. So that was really strange to us. So we took our film and took it to the synchrotron with our collaborators in Argonne National Lab. they did some tricks because it's very, very hard to distinguish magnetism in thin film from just regular scattering, because you have charge and you have a spin. So there is a trick. They invented a new trick doing polarization analysis of X-rays. So where they could see if you particularly polarize your light in this way, like this, and you analyze light like that, then you will see only spin. So light, incoming light, you have polarization like that. Then after the scattering, you should analyze it with the polarization like that. Then you detect your light, scattered light, X-rays, and then you will see spin only. So I think that's the reason people couldn't see it and report it. So we use this trick, and I'm showing you the result. This is the magnetization as X-rays sees that. So this is the integrated intensity of scattered light, which is proportional to the magnetization. That's the temperature. And you see a very beautiful long-range order, like you expect in the antiferromagnet, and that's particular Q vector. So this is the very first report that's what we're reporting today, of this exotic all in, all out, this 4-in-4 magnetic order in this Weyl semi-metals. So now it's not the imagination. Now you can really be very confident that these materials they have the transition into this unique all in, all out antiferromagnetic state at this temperature. And it really coincides with the transport you measure in your resistivity. So it's very beautifully sort of coherent with the same number. Okay, and now the key. Do we have Weyl fermions, right? Show us the Weyl fermions, because that's all interesting. And what I want to demonstrate is there a bizarre thing called the chiral anomaly, which we borrowed from particle physics, high energy physics. And then is there any anomalous Hall effect due to Bare phase? Because remember, this is antiferromagnet. It has no internal magnetic field. How can you have Hall effect without magnetic field? Zero magnetic field, zero internal magnetization. How can you have Hall effect? And the only answer, you have a curvature in a momentum space, right? Where the electron moves and it produces fictitious magnetic field. So that's what we want to demonstrate. So first, chiral anomaly. Chiral anomaly is a very bizarre phenomena which has been proposed in 60s in the particle physics to explain some strange abnormal masses of the particles. So I'm not going to go into that. But then two people, Nielsen and Nina Meyer, proposed that you can see Weyl fermions in the crystal. Well, that was quite strange because it was 1983. Nobody thought about that. But what they said, take a crystal and really increase magnetic field a lot, make it really, really high magnetic field. And then in your material, if you have Weyl fermions, you have very special Landau levels. In a high magnetic field, you this is the Weyl knot, and this is another Weyl knot which has Weyl knot chirality +1, another Weyl knot chirality -1. So here you have two Weyl nodes sitting next to each other. Or you can think about this is the North Pole, this is the South Pole, so they sit to each other. And in the high magnetic field, these monopoles, they basically they will go into the linear dispersing things, like in the Dirac particles. So it's a linear dispersing thing, like in a relativistic Dirac particle, and that's the only state which is fully occupied here, and fully unoccupied there. Everything else is empty or fully occupied. So if the scattering or some kind of current will occur, it should move electrons between those two. And then what they say, okay, so this is what magnetic field does. It produces this kind of Landau levels. And then you apply electric field. And then this electric field, of course, electrons move against electric field and they start moving this way. Okay, so the electrons start moving that way. But that means, in turn, that you're moving electrons with the chirality of those Weyl fermions. They have chirality +1 and the chirality -1. And that's what's called the non-conservation of Weyl fermionic number, because here the chirality is changing and you're pumping the electrons with this chirality into electrons with that chirality. It's a very, very strange thing, right? And it's called the axial current. And there's this very new kind of electrodynamics called the axial electrodynamics. And what's most important is this current is proportional to the electric field dot, not cross, but dot magnetic field. So in other words, it's a cosine between those two. And it's really the largest when they parallel. Okay, so here I'm going to report, it's the first time I'm showing this graph. This is the baked right out of the machine. Our result, this is the chiral anomaly in our European Meridate 1-1 oriented thin film. This is the conductivity, I remind you, is proportionally dot B. So what we've done, we run the current here and apply magnetic field, and we rotate the magnetic field. This is the degree. And as you can see, once the magnetic field is 9 Tesla here, you see beautiful cosine oscillations as I predicted. And really, this is the whole effect. This is the rho XY. So this is the transverse resistivity, like in the whole effect. And it oscillates as predicted by the chiral anomaly. This is the axial current. So it's a fully topological result. And once you turn it off, it's a control check. Of course, it disappears, right? So it's not some funny magnetism sitting inside. It's really like what the chiral anomaly. So to my knowledge, this is the first result, which is clearly shows the presence of chiral anomaly in this 1-1-1 oriented film. Maybe somebody else is also measuring, but to me, it's very sort of vivid result. Another result which I want to just finalize right now is to show this is the pair of Weyl knots, and what are we doing? Because I just remind you, so even if you have magnetic field m equals 0, but you have non-zero curvature of momentum space, right? It produces fictitious magnetic field, right, inside. And that magnetic field inside, due to this pair of Weyl fermions, Weyl knots, this been shown even in 60s by Karplus and Lottinger, is really is the result. This is the conductivity in x and y direction. So it's a transverse conductivity. Is really the distance between two Weyl knots in the momentum space multiplied by the Chern number, or the chirality of these things. So it means that if you measure the conductivity anomalous Hall effect in this crystal, then you should see strong anomalous Hall effect, even though magnetization is equals to 0. Okay, in this material. And this is the calculation which has been done by our collaborators, which shows really indeed the magnetization equals to 0, but Bare curvature in this pyrochlore thin film, the brighter area, the larger Bare curvature. So it really, you can see that's how the magnetic field is really distributed due to the curved momentum space. Okay. And that's the result. So if you use this Bare curvature, you just integrate it out and use the previous formula, you got the conductivity. This is the conductivity map in real space in the film. So it's the top view. And so I want to show to you the experimental result to finish my talk. So this is where the material is non-magnetic. So the Weyl knots not appearing here. It's just control check. This is the anomalous Hall effect resistivity here. And then it becomes magnetic, and you can clearly see there is a beautiful anomalous, so it's a hysteresis. Even this is the 0 magnetic field. So in the 0 magnetic field, you can see this hysteresis is really like as if you had the magnetic materials, like if you had a ferromagnet, right? Though I want to remind you again, this is an fully compensated anti-ferromagnet, which is m equals to 0, and it cannot have this kind of hysteresis unless you really truly use the Bare curvature as a source of internal magnetic field, which is a kind of pseudo Lorentz force, if you wish to. But in reality, it's really the topological current, and it really got gigantic. 23% of quantized conductivity in this material. So, and that I want to finish. There are a couple of references which describes this all what I just reported. And thank you very much for your attention. And my apology if I was writing. I was not writing too late, right? I guess with all the introduction. But given that I do it the first time, this kind of talk, so I think it's excusable. All right, thank you. I'm done.
Okay, great. Thanks for the excellent talk, and also I learned a lot. I worked a little bit on this field, especially my previous research group worked on this related topics. I know this kind of growth is extremely challenging. For example, my previous group, they worked for years on those types of material. They could not get a good film. So I know how hard this topic is and how difficult to get excellent crystals. Now the session is open for questions. Maybe I ask one short questions to warm up the session. Prof, I have a question related to the surface states in at oxide surfaces. People work on oxide interfaces, oxide surfaces. They often observe some insulating non-magnetic states. Typically, a lot of people call it dead layers. My question would be, in your opinion, do you think it is an intrinsic phenomena or it's extrinsic phenomena that happens after we take out the samples out of the vacuum or something? And how would it impact in the future, like measurement characterizations or even applications? Because I think you are trying to do in situ measurements, and yeah, so how would you either tackle the problem or solve the problem? Yeah.
I think it's an excellent question without the universal answer, because I'd like to make a comment that very often I think we oversimplify the problem, even including graphene. People do claim this and that. In reality, if you do your self measurements, you do know that how important to keep your even graphene, which is very robust, to be clean. Transitional metal chalcogenides are absolutely sensitive to oxygen. So the chalcogens, so another poster boy of the modern quantum condensed matter physics, this ultra thin monolayers of chalcogenides, they're extremely sensitive to the surface. So it immediately raises the question of real applications and that kind of thing. Now moving to oxides, right? Oxides typically the multi-component materials, they're not terribly sensitive to oxygen because they already contain oxygen, but they're extremely sensitive to typically to water. So water would be another thing, but I would say you have to go from material to material. You know, there is no universal answer. However, what we found really peculiar with the advantage of in situ growth and ability to measure with ARPIS electronic structure, we look at some of the surfaces which I didn't believe they should survive more than several hours. In reality, we still could see Fermi edge, not maybe band structure because that sort of disappears fast, but even Fermi edge for more than a day and a half before we sort of lose the surface. So the problem of that layer exists, and I think it depends on the specific material. And I find one of the facts which is still not resolved is that practically every single thin film oxide multi-component becomes non-metallic and non-magnetic below 4 unit cells. That's my sort of brief answer.
Yeah.
So, but it's a very good question, but it's maybe a subject for a separate talk.
Okay. So may I know whether there are other questions from the audience? if you want to ask the questions, if you are too shy to ask, you can also type your question in the chat window. I see Alex.
I have a question, if I may, please.
Alex.
Hello, Jack. Nice to hear from you again. Thank you for the nice talk.
Yeah, nice to see you too.
You too. I have a technical question and a general question. For the nice X-ray scattering data that you presented, which absorption edge are you using there, and what's the X-ray?
This is L3 iridium. Thank you for asking this question. Yeah, this is the L3 iridium, so it's directly probing these states.
Okay.
Yeah, it's about 11 kilo electron volts.
Okay, that's great. So in the
yeah,
hard,
the details of
range.
all the details are posted in this. Yeah, so as you can see can you see that?
Yep.
Yeah, so this is
I
11.
missed that. I'm sorry. Yeah.
Right. Yeah, 11 point. No, that's fine. It's 11.2. That's the L edge. So we're really looking at the iridium.
Yep.
It's just it's a direct measurement.
Okay. And as a general point, are there any interesting dynamic properties of this all-in, all-out order? So, for example, if you were to drive it with a microwave excitation and create some kind of resonance, how would this influence the chiral anomaly that you see afterwards?
Oh, that's very good question. This whole field of axial electrodynamics is there. you can look at the numerous Peter Armitage to write long reports about this axial electrodynamics. The most important thing is definitely microwaves will have a specific response. I don't know the details about microwaves, but for example, you can do you can use terahertz radiation, right, and try to measure Faraday rotation in terahertz. We see a very large response. But that's sort of hallmark of this relativistic fermions. With this chirality drives the thing, this axial currents. They really produce very large the responses in terahertz when you do the Mach kind of measurements. Also, you can you can look at the plasmons, for example. This chirality, is a real thing, because now you start coupling to one kinds of electrons, not coupling to another ones. So this kind of misbalance is really what I mean. With the availability of material, I think it's open for the things, but I don't know. I know the RIX was done, so people see the excitations. For example, one other thing. This material, it has topological magnons. So in other words, topological means the magnon bands, they are Weyl. So even in the bosonic spectrum, we see the Weyl crossings in magnons. So if you can drive them with the microwave, for example, that perhaps you will see something very peculiar. So that's another thing I didn't talk at all, right? So this is different sort of topic. This structure not only has an electronic spectrum, but also in the spectrum of spin excitations. That's sort of peculiarity, if you wish to, Alex.
Yeah, that's well, potentially very promising. Thank you.
Yeah, it is. It is. Yeah, it's very interesting. Good question. Very good question.
Okay. Do we have more questions? If you have questions, you can also email Prof, and you can find his website, I think easily from Google. And I think looks like no more questions.
Can I just ask a question?
Okay, sure.
Okay, thank you very much for the talk. It was very wonderful. So I'm not at all an expert in condensed matter physics. I know a bit of topology. And I mean, I was interested by this anomalous Hall effect. I mean, for me, it's very surprising somehow that it can survive at such a high temperature. I mean, is it correct, or I mean, is it really special for your material, or do you have other material that can have even this effect at higher temperatures? So that's my first question. And related to that, I mean, so is it due to the fact that you have a very strong spin orbit coupling here?
Not really. I'll show the slide which I sort of skipped, and I'll show just one graph instead of saying many words. If you just look at me, just let me show to you why it survives. I want to show to you how the paramagnetic phase look like. So this is the paramagnetic phase. It's actually a semi-metal. Even when it's non-magnetic, it's a semi-metallic. It's known the Latinger, Abrikosov, and the B, I don't know, it sounds like Bulaevsky in my memory, but the LAB state. So this is really a quadratic band-touching paramagnetic phase. And what happens here, once it goes ferromagnet, anti-ferromagnet, and it doesn't matter what temperature, right? So it could be 100 and 200. What happens then, majority minority bands split, right? So like this. And you have no chance not to create Weyl points. If you start with this state and you split these bands, then they just basically have these crossings automatically. And that's the reason they survive such a long thing. So what protects them really the magnetism. So as long as this magnetism is not, I mean, of course it's spin orbit, right? The high spin orbit and the moderate Hubert U creates this very unusual structure which automatically generates this Weyl crossings. Of course, if you start making material more and more magnetic, going to low temperature, what may happen, this Weyl points start moving because that's basically, they just repulse them to the edge of brilliance zone. And once they reach the edge of brilliance zone, of course, they annihilate because they have different chirality and boom. So what it means, then the gap opens up. So it becomes just trivial, trivial insulator, of course, with the Mott insulator, okay? But topologically trivial. So to answer a very interesting, good question, a lot of insight in there. If you start with this unusual phase and this pyrochlore, right, you end up always with the Weyl phase once this specific antiferromagnet sets in. But it also requires the spin orbit because the band structure is specific, right, to generate this. Plus, it needs to be very moderate magnetism. Otherwise, you just push them to the edge of brilliant zone. And that's the reason a lot of the antiferromagnets, they just trivial Mott insulator, just correlated magnets, non-topological. But if you could somehow dynamically, for example, by using light or microwave, reduce the basically introducing spin fluctuations, right? For example, if you could reduce the value of magnetism, then you still could push them back into the brilliant zone. And you would have many more dynamically generated Weyl crystals. It's just an idea. So the German theory group from Dresden actually has a wonderful nature com how to do it with the light. Basically, they just apply the light to fluctuate spin. So that's what, yeah, you're correct. So it is. So it's surviving because the paramagnetic state is kind of unique. But otherwise, you're correct. Yeah.
I see. Okay. Thank you.
Okay, great. I think for the interest of time, we have to stop for now. If you have other questions, just contact Prof. Chakhalian. And again, thank you very much for the excellent talk, and we look forward to future interactions with you. And thanks a lot. Thank you, everyone.
Thank you very much, and I really happy to talk to and see some of the colleagues I met before. Thank you very much, and hopefully we'll see each other soon in three-dimensional world.
Yeah.
Okay, thank you.
Great.
Bye-bye.
Yeah, bye. Thank you, everyone. Thanks. Bye.
Bye.